What's going on, smart people? Today's video will go down in history because we are solving one of the most important problems ever addressed in physics, brought up by none other than Tony Stark in Avengers Endgame. If you haven't seen the movie, that's fine. We're not going to be getting into any spoilers in the sense that knowing that Tony Stark says something smart sounding isn't a spoiler, that's kind of a given. And we'll be talking about it without any context, so if you haven't seen the movie, you'll be fine. But in it, he asked Jarvis to give him an image of a Mobius strip, invert it, and then find its eigenvalue. And I'm going to be showing you how to do that today. Now, first things first with the whole invert it part, I think he just meant, like, turn it physically. So we're going to be ignoring that and just focusing on the Mobius strip eigenvalue part. Now, if you don't know what a Mobius strip is, this is just a rectangle, and if we connect both ends of the rectangle, we get a cylinder. And for a cylinder, you can go around it one time and get back to where you started. And with a Mobius strip, you twist it once before you do that connection. Oops, there we go. And when you do that, you actually have to go around twice. Here's once, and here's twice to get to the same side. In other words, to rephrase that, going around just once gets you on the opposite side of the sheet. But when Tony Stark said it, admittedly, when I first heard it, I thought he was just stringing together nonsense like science words to make himself sound smart. But after thinking about it for a while, I realized, no, we can do this. You can conceptualize some quantum particle confined to a Mobius strip and maybe solve the Schrodinger equation for it, whose eigenvalues would just be the energy of the particle for a given eigenstate. So that's what we're actually going to be doing. And after speaking with my professor, there's actually another layer to that you can go where, because we're effectively just going to be taking a rectangle with Mobius strip boundary conditions. But what you can do is you can physically embed, you can actually embed the two-dimensional surface into a three-dimensional space where things like the orientation of the particle and of the surface really matter. And that makes things a lot more complicated. Like, how do you introduce spin? Like, if you have a particle going around a Mobius strip, then at some point the spin is going to have to flip. It's not constant. And I think an active area of research is actually making these Mobius strips, or trying to make these strips from graphene, and then study the electron wave function on the graphene Mobius strip or something like that. I don't really know. But there's another layer that's much more complicated than what we're going to be doing, which is just something to keep in mind. So the first thing, let's just draw. So here's our rectangle. And we're effectively just solving the particle confined to a rectangle with Mobius strip boundary conditions. But what are those? And that's actually what makes this problem so interesting, is the hardest part of this problem is usually the easiest part in solving the Schrodinger equation, just specifying what the boundary conditions are. So if we have a rectangle that's some length L and say some width W, when I did this earlier, I used H for the W, and I got super confused on what my H bars and H's were, and I ended up having extra factors of H bars. So we're going to call that W. But here's our L and our W. What I want you guys to do is, in Cartesian coordinates, that's how we're going to be doing this, is I want you to see if you can figure out what these boundary conditions should be for the wave function. Hopefully you've just taken some time to try to figure out what those boundary conditions are, so let's see what they actually are. The first one is the easy one. The first one's easy if you think about the infinite square well. There's nothing keeping you from talking about the wave function outside of the boundary. It's just that the value of the wave function has to be 0, because it's the infinite square well, it can't leave. But since we want our wave function to be continuous, we couldn't have continuity if the wave function value at the boundary was anything other than 0, because then there would be some kind of jump there. So the wave function at the boundaries has to be 0, and in the exact same thought process, it has to be 0 for the y boundaries here, because it can't leave the strip, but it has to be continuous, so the value at the boundaries must be 0. Okay? So the first one says that psi for any value of x, but at the y boundary, so 0, x, y, or, see, that's what I did last time, was I used h all the time. W is equal to 0. So that's one of the boundary conditions. The next one is a bit more subtle, but we just have to incorporate the fact that if you go around once, you get to the opposite side of the strip. Okay? So for that, if we start at any value of x, but then we go L more in the x direction, we should be on the opposite side. So L plus, or x plus L for any value of y should get us back at x, but on the other side, which we'll denote with the minus y.
Wrong.
That is absolutely
wrong.
Proved over and over again.
Wrong.
We actually
Wrong. Very nice words, but happens to be wrong.
Wrong.
Future bigger brained Andrew here. I had to delete the video that I posted yesterday that had the clip that you just saw along with the actual calculating the eigenvalues of the Mobius strip, because as some of you pointed out in a very nice way, I made a mistake. These boundary conditions together are not correct. And let me try to shed a little bit of light on that. It stems from the whole, what am I calling the boundaries in the first place? If you were to take this Mobius strip and say you start on the red dot, which I hope you can see, and then you go over one distance L, you will end up on the other side where the blue dot is. Now, where is the location of that blue dot? Well, if we're going from 0 to W, if we're starting at 0 and our y ends at W, those are our boundaries, then this blue dot is going to be, let's call this some distance y. So this is y. So then the blue dot is going to be the distance W minus the distance of y. So this is going to be at W minus y. So if we insist on using those coordinates, our correct boundary condition would actually be psi of x plus L y is equal to psi of x W minus y. Now, you can go through all of this and do the calculations and go through the algebra. I did it too, and it is miserable. It is disgusting doing it this way. This is correct, this is a good way, or it's a valid way of going through it, but it's very tedious, and I don't recommend it. Instead, what we're going to do is we're going to shift our coordinates. Instead of going from 0 to W, we are going to go from W minus W over 2 minus W over 2 to W over 2. So the width is still W, we're just shifting our coordinates. And now we have a Mobius strip that's centered at 0. So if you're at y here, the blue dot is just at minus y. So this boundary condition still can hold if we use minus W over 2 to W over 2. The only thing is this boundary condition now has to change. So you can do one or the other, it's just you can't impose one without changing the other boundary condition. So we're going to be using this one here, and we're going to be changing this boundary condition to minus W over 2 to W over 2, and we'll be carrying forward with that. So I hope that makes sense. I'm sorry for the mistake. And again, like I said, I really appreciate how respectful everyone was with correcting me or pointing out the mistake, because the internet is usually not very forgiving. So at any x at minus W over 2 should be equal to psi at any x at W over 2, which is equal to 0. And now these are the correct boundary conditions. And in some sense, this doesn't change the solution too much, and in another sense, it almost makes it another problem to solve. I'm going to take a sip of coffee because I've been trying to explain this to myself all morning. Okay. So if these are the boundary conditions, the next step is to solve the Schrodinger equation. The Schrodinger equation, or rather the wave function that you solve for, is defined by having a unique potential or a unique boundary condition. So now that we have that and we don't actually have a potential, our Schrodinger equation in Cartesian coordinates is just minus h bar squared over 2m d squared over dx squared plus d squared dy squared. It's going to be acting on the wave function psi of x and y, but we're already going to assume that we can separate variables. I hope that you guys are familiar or have seen separation of variables before. Basically, we assumed that we can split this wave function into a function that depends on x and a function that depends on y. I don't know, to be honest, if there is a rigorous way of saying, no, this is always a valid thing to try to do, but I've always heard it as like losing your keys outside in the dark and searching for them under the street light. It's like you don't know that they're going to be under the street light, but if they're not there, you're not going to find them. Similarly, if we can't separate variables, well then we couldn't solve it in the first place, so we might as well try. So we will assume that the wave function is just the product of a function of x and a function of y. So instead of writing psi of xy here, we're just going to write f times g, where you know that this depends on x and this depends on g. And this will be equal to the energies times F times g. Okay, I'm going to erase this. Let's distribute everything out, because we don't skip steps here, because apparently then we make mistakes. So let's go ahead and multiply the 2m over h bar squared minus onto this side and distribute these derivatives. So to the i's of the x derivative, the g is going to be a constant because it depends on y, and to the i's of the y derivative, f is constant because it depends on x. So we get g d squared f over, and this is actually going to be a total derivative. I'm minding my p's and q's in this video. I don't want to make any more mistakes. Plus f d squared g dy squared is equal to minus 2m e over h bar squared fg. Then dividing both sides by the functions on the right hand side, we get a 1 over f d squared f dx squared plus 1 over g d squared g dy squared is equal to minus 2m over h bar squared. And then we have this E, we have this energy, this total energy, and that total energy is going to have contributions from the x part of the differential equation and the y part of the differential equation. So we're going to denote that with an EX plus an EY from both of those contributions. Okay? And this is a constant, and these are derivatives and functions of different variables. So what this tells you is that if this is a constant and we're adding these two things together, then these two things individually must also be constants. Because if they weren't, if this still had some x dependence, there'd be no way to eliminate that x dependence by adding to it something that possibly depends on y. So both of these must be constants, and we can give a name to those. So let's go ahead and call this one minus kx squared, and this one will be minus ky squared. I'm doing the minuses so that I don't have to worry about this minus sign here. And up top, what that tells us is that h bar squared over 2m kx squared plus ky squared is equal to the total energy. So that's all that we're saying here. And we're going to use this to find the total energy later once we're actually, because the energy is just going to be the eigenvalue. It's the eigenvalue for a particular eigenstate. Okay? So let's go ahead and set these derivatives equal to the constants, and we're going to have two differential equations. So over here, and I'm sure I'm going to end up erasing some of this at some point. So the first differential equation, we have a 1 over f, a d squared f dx squared is equal to minus kx squared. Multiply this over, we get 1 over f. I just said multiply over and I didn't multiply over. F double prime, I'm just going to drop the d's, plus kx squared f is equal to 0. So we get that the function must be proportional to its derivatives, or its second derivative. That's the definition of an exponential. So the procedure is you guess that f is some exponential, e to the some lambda x. And you substitute this into the differential equation, which is going to give us a lambda squared e to the lambda x plus kx squared e to the lambda x equals 0. The exponentials are never 0, which means that the contributions that make this 0 must be the lambda squared plus kx squared, or in other words, we're dividing out the e to the lambda x. So we get lambda plus kx squared is equal to 0, which tells us that lambda is equal to plus or minus I kx. Using Euler's identity, we can rewrite this complex exponential in terms of sines and cosines. This is a second order differential equation, which means we'll have two constants of integration. So f is just equal to some constant 1 times cosine of kx times x plus constant 2 times the sine of kx times x. Okay. Normally using Euler's identity, there's the I, but the I can just be absorbed into the constant. Now the second differential equation here is the exact same one. So there's no need to solve the same thing twice. Just swap f with g's and x's with y's. So g is just equal to some constant 3 cosine ky y plus some fourth constant sine ky y. So if you saw yesterday's video, nothing's really changed so far, and it won't until we impose the boundary conditions, which is kind of like right now. Okay, so in this boundary condition right now, we have that for any x, y evaluated at these guys, the wave function should be 0, which means that out of the product of the f and g, this is equivalent to just the g of minus w over 2 equaling 0 and the g of w over 2 equaling 0. Just the function of y, because that's the part that has to make the whole thing 0, since it works for any x. So let's go ahead and substitute this boundary condition into the g. So we get g of w over 2. I'm not going to write g of w over 2. Let's just substitute this stuff in. So we've got c3 cosine ky w over 2 is plus c4 sine ky w over 2 is equal to c4. So if we're doing minus, well, cosine's an even function, so it doesn't feel the minus sign, so it's just going to be a c3 cosine ky w over 2, and then sine's an odd function, so there's the relative minus sign when we substitute in the minus w over 2, c4 sine ky w over 2. It's always weird making these kinds of videos because I'm like, oh, maybe these people know separation of variables. Do they know what an odd function is? Because I have high school students and college students and grad students, students of all shapes and sizes probably, so I never know what I need to explain. Okay, so this is just boundary condition here. This is just boundary condition with the minus w over 2, and the c3's cancel. So we have nothing really right now constraining these terms. So this is just saying c4. Actually, let's kill two birds with one stone. So the c3's cancel, and then we can just add this guy over to this one. So we have 2 c4 sine of ky w over 2 is equal to 0. The 2 can be divided out, and we have this here. So there are actually two options that can make this 0. I erased the stuff up here because we're going to need some space in just a little bit, but we have two options. Either c4 is equal to 0, or the sine of the angle is equal to 0. So there's two cases. So let's break it down to case by case. So case 1 says that maybe just c4 is 0. And if c4 is 0, then the g at the boundary still has to equal 0. So we have that g of y is equal to c3 cosine of ky y, and at the boundaries it should still be 0, so at w over 2 and minus w over 2, but now that we're only dealing with cosines, the minus doesn't matter, is equal to c3 cosine ky w over 2, which is equal to 0. So this is going to be 0 if c3 is 0, but that's boring because that would mean g is 0, which would make the wave function 0 for all values. So it's got to be with the angle. And when is the cosine 0? The cosine of an angle is 0 for odd integers of pi divided by 2. Right? Cosine of pi over 2, cosine of 3 pi over 2, and so on. So this tells us that ky is equal to, let's do kyw over 2 is equal to an odd integer, so we'll denote that with a 2n plus 1 pi over 2, okay, which tells us that ky is equal to 2n plus 1 times pi divided by w. Alright, so for case 1 we'll go ahead and put that up here. Ky is equal to 2n plus 1 pi over w. And let's make ourselves a little bit more space. So case 2, let's look at case 2 now. And we'll underline this so we know these are the cases. Okay. Case 2 is if the angle makes the expression 0, which tells us that ky w over 2 must be just some integer times pi, n pi. In other words, ky is equal to n 2n pi over w, right? Yeah. All right. So now, that doesn't say that C4 has to equal 0, but it does fix what ky has to be at the boundary. So let's see what that does to sorry, not C4, to the C3 term. So let's go ahead and erase this. Okay. So we know that for case 2, ky equals 2n pi over w. So at the boundaries, that term is going to be 0 because we just chose ky to do that. So g at w over 2 should equal c3 cosine ky, which is going to be a 2n pi over w, times y evaluated at the boundary, which is w over 2. So these cancel, and we get c3 cosine of n pi equal to 0, because it has to be equal to 0 at the boundaries, and the second term is automatically 0 because we chose ky such that it was. Cosine of n pi is either going to be a 1 or a minus 1, so the only way for this to be satisfied is if c3 is equal to 0. So for case 2, we get ky is equal to 2n pi over w, and c3 is equal to 0. Great. Now we have all of the pieces of the puzzle to start stapling together our f's and our g's in a wave function and tackle the other boundary condition. So let's go ahead and do that. Okay. This stuff is going to look really messy and cluttered very, very fast. I guess I'll erase the algebra and write the wave functions and stuff, and then we'll move on to the next boundary condition. Okay. So all I've done so far, or all I've done right here, is I've just made a little bit more space for myself. These are our two cases where we have our different g parts of the wave function and our different values of ky. One where effectively you could rename this to some n where n is odd, and this to some n where n is even. Okay, now let's put everything together. So if we want to impose this boundary condition, we have something that's has x different and y different, which means we can't just treat f, we have to put it all together. So our wave function, psi of x and y, is going to be different for these two cases. So let's go ahead and partition everything off. Okay. I will use all the space I can. So for case 1, what is our wave function? Well, our wave function is going to be our f times our g. So psi of xy is equal to, I'm going to define a1 is defined to be c1 times c3, and I'm going to define a2 to be c2 times c3, and I guess I'll end up having to do the same thing for the other case. So say a3 is defined to be c1 times c4, and a4 is defined to be c2 times c4. Just because when I multiply these together, these coefficients attached are going to be distributed to these guys, and I don't want to just write those. Let's just define new variables. So for case 1, this is going to be an a1 cosine of kx x kxx cosine ky y plus a2 sine of kxx cosine ky y. So this is what we need to impose these boundary conditions for. So let's go ahead and do that now. So we have, for these boundary conditions, a1, I'll move over here, a1 cosine kx x plus l cosine ky y plus a2 sine kx x plus l cosine ky y is equal to, well, now it's just the x at minus y, but for our minus y, we're plugging that minus y into cosines, so nothing changes. So this is just going to be, and I'll write this down here, I suppose, which is equal to a1 cosine kx x cosine ky y plus a2 sine kx x cosine ky y. And you see that we have a common factor of cosine ky on each of these terms, so we can get rid of that, and we get that this a1 cosine kx x plus l plus a2 sine kx x plus l is equal to a1 cosine kx times x, and then just plus a2 sine of kxx. Alright, make sure that my camera's still going because it turned off on me. So this side has L's, this side does not have L's, so this whole point of case 1, case 2 is to try to fix what our kx's have to be now. Because that's the whole point, we want to find our energies, and those are in terms of the kx's and ky's. So since this doesn't have L dependence, our k over x must be proportional to some 1 over L, and we can actually make our life pretty easy by noting that this should hold, these boundary conditions should hold for any value of x. Okay, so it better hold for x equal to 0. So let's go ahead and consider that real quick. If we consider x equal to 0, we see a1 cosine of kxl plus a2 sine of kxl is equal to, well, a1 cosine of 0 is 1, so we've just got an a1, and sine of 0 is 0, so that doesn't contribute. So there's no a2 over here. For whenever we want to actually, or if we wanted to actually find out what all these constants were, one we'd have to fix with the normalization, but here we can actually solve for a2 in terms of a1 if you wanted to do that in the future. We're not gonna, nope. So, but we need this term to vanish, and this term, we need this term to vanish because there's no a2 over here, and that can vanish if a2 is 0, but also if just the angle is some integer multiple of n pi, which we need anyways in order to get this a1 by itself. So at least kxl needs to be n pi. This tells us that it needs to be an even integer times n pi because there's no minus sign over here. So this says that kx times l is equal to 2. Let's not reuse n, let's call it, do I want to call it little l? Let's just use little l. Why not? Little l times pi, right? Yes. So then kx is equal to 2l pi over big L. Again, this is for case 1. So now that we have a nice little case 1 thing, let's go ahead and plop this over here. I guess we don't really need the picture anymore. So let's put the energy relation over here. H bar squared over 2m kx squared plus ky squared is equal to E. Yeah. Okay. So for case 1, now we have kx is equal to 2l pi over big L. For big L. Awesome. And now we can deal with case 2, and then we'll basically be done. So in I think when I did it last time yesterday, there weren't 2 cases. There was only 1 case, which makes things a little bit more complicated for us. Or not more complicated, just more tedious. So now let's go ahead and consider case 2 and do the same thing. And to not have confusion, let's just go ahead and call these B's instead. B1 and B2. Cool. So sine of xy for case 2 is going to equal B1 cosine of kxx times case 2, which was sine of kyy plus B2 sine of kxx sine of kyy. And let's go through the exact same motions. So we have B1, let me just stand right in front of the camera, B1 cosine, after evaluating the boundaries, cosine kx x plus L, sine of kyy plus B2 sine of kx x plus L sine kyy is equal to B1, well actually no, so here we're putting in minus y, and sine is an odd function, so the sine of the minus is equal to minus of the sine. So we get minus B1 cosine kxx sine of kyy. Same thing goes here, minus B2 sine of kx x sine of kyy times y. And again, just like last time, the y terms cancel because they're on each of these, and this simplifies a little bit to B1 cosine kx x plus L sine of ky, nope, I just said that they cancel, plus B2 sine kx x plus L is equal to minus B1 cosine kx x minus B2 sine kxx. Fantastic. Anything clear here? No, so now we're running into the same thing. We've got L's on this side, no L's on this side, so our kx has to be proportional to 1 over L. And we're going to do the same thing where we say, well, let's consider x equal to 0. So for x equal to 0, then we have B1 cosine kxl plus B2 sine kxl is equal to minus B1 cosine of 0 is going to be a minus B1, and then this is going to be a 0. So we need this to be 0, so it has to be some integer multiple of 2 pi. This kxl has to be some integer multiple of 2 pi, and we need to pick up a minus sign when we do it, so it needs to be an odd integer multiple of 2 pi. So that tells us that kxl is equal to 2 2L plus 1 pi. Okay? In other words, kx is equal to 2L plus 1 over big L, or we can write this as 2 pi over L times L plus 1/2, which is just a normal way of writing these kinds of things. Cool. So now we have our kx's for both cases and our ky's for both cases, so we can finally find out what is the eigenvalue of a Mobius strip. Well, when Tony Stark asked Friday that, apparently it was Friday, not Jarvis, I'm sorry if you saw the last video, Jarvis should have said, for what eigenstate, you dumb, never mind. But it depends. It depends on this n, or it depends on n, and it depends on L, so it's not just the energy, it's going to be the energy sub NL. So if we look at that, so En L is going to be equal to, we've got our h bar squared over 2, that's an m, don't let anyone ever tell you that's not an m. That's across the board, h bar squared over 2m, and then we're taking it case by case. I'm sure there's a more concise way to write this, but I can't be bothered at this point because I've made this video twice. Okay, so for case 1, we know what ky is and we know what kx is, so this is going to be a 2L pi over L, big L, squared plus 2n plus 1 pi over W squared. So that's for case 1. Case 1, or you could say for odd n, or something like that, if you wanted to split it that way. And then the second one is going to be, so we've got our ky, our kx is right now. Where's our kx? Our kx is right now. It's going to be a 2 pi over L plus 1/2 squared plus the ky squared, which is going to be a 2n pi over W squared. There we have it, ladies and gentlemen. There is the energy for the NL eigenstate for a particle confined to a rectangle with Mobius strip boundary conditions. This is a pretty cool problem. I wish I didn't make a mistake the first time, but I'm happy you guys stuck with me and didn't destroy me for making a mistake like most people do for the internet, right? But this is a cool problem because when we think of solving the Schrodinger equation and the limited number of problems we can solve by hand, we normally attribute that to the potentials. There's a limited number of potentials we could introduce that we could still solve by hand. But you can also change the problem by changing the boundary conditions. And at least for people like me, apparently asking what the boundary conditions are is a good problem as well. So I hope you guys enjoyed the video. Let me know in the comment section if you did, and I'll see you guys there. Also, thanks for 69,420 subscribers.